In this lesson, we're going to be talking about some basic electricity and the concepts of alternating current. Now, alternating current is the current that's found in your plugs in your houses and buildings. Direct current is basically what's found in car batteries and some of our technology. Most of our computers and everything is built on direct current. So we have two types of current. We have alternating current and direct current. So back to the basics. Current is a flow of electrons. DC current is an electron flow that occurs only in one direction, from a positive to a negative. Alternating current is a back and forth flow of electrons that first goes positive to negative, then positive and negative shifts, and it flows the other way, which means the electrons reverse their direction of flow at regular intervals. DC current is not as common as AC because it's only used in certain applications. Most of the current produced by the electric utilities is alternating current. Most of the equipment in the HVAC industry runs on alternating current, as do most of the items in the home. Okay, one of the biggest benefits, and the reason this is because there's money involved. It's cheaper and more trouble-free than equipment that runs on direct current. However, you have much more control over things like motor speeds, exact voltages and stuff like that with direct current. So you have a trade-off. Okay, since alternating current is most widely used form of current, we have to really understand how it works and the theory behind how it works. It will make understanding your meters much easier. Okay, you should also be familiar with the way it's distributed by the power companies. So alternating current, or AC for short, is an electron flow that alternates. The electron flows in one direction and then in the opposite direction at regular intervals. Alternating current is produced by cutting a magnetic field with a conductor. So what we do is we spin a magnet inside a coil of wire. The coil of wire is the conductor, and the magnet produces the magnetic field. The sine wave is used as a graphical representation of AC current. So this is a sine wave. Now what's really important to remember is that one wave cycle is basically 360 degrees. Okay, we go from 0 degrees to 90 degrees. Then we add another 90. That comes back to 180. Then we go to 270. And then we come back to 360. So one sine wave is 360 degrees. However, one wave cycle is from a negative back to a positive, back to a negative. Okay, so that's one wave cycle. However, again, this 0 to 360 happens 60 times a second. And the measurement of that is hertz, H-E-R-T-Z. So when the conductor rotates through one complete revolution, it has generated two alternations or flow reversals. That's one cycle. One cycle occurs when the rotor or conductor cuts the magnetic field of a north and south pole of the magnet. The frequency of alternating current is the number of complete cycles that occur in a second. That frequency, as I mentioned, is known as hertz. H-E-R-T-Z, or shorthand, capital H, lowercase z. But it's also referred to as cycles. The most common frequency in the United States is 60 hertz. But in some areas, in sub-Saharan countries, 25 or 50 hertz is used. A 25 hertz circuit can be detected by human eye in light fixtures. The 60 hertz cycle is most common, but 50 hertz is used in some cases. Okay, the phase of AC circuits is the number of currents alternating at different time intervals in the circuit. Single phase has only one current, like the picture that I showed you of the sine wave. Three-phase current has three separate currents. Alternating current is available in several voltages, all with different current characteristics. You have two 30-volt single-phase 60 hertz. 230-volt three-phase 60 hertz, 208-volt three-phase 60 hertz, and 460 three-phase 60 hertz. Notice the single phase really drops out after the 230 volts. So looking at this sine wave, it's very different than the single phase that I showed you a few slides back. Okay, this is a sine wave for three-phase current. Okay, the blue is phase 1, the red is phase 2, and the green is phase 3. Now, the key is that it's still alternating between negative 120 and positive 120. So this is a 240 volt circuit. However, you'll notice that no two phases, if this is going across time, you'll know that no two phases are at 0 volts at any one point in time. So for example here, at the second part of the 1/180th of a second, green, which is the phase 3, is in 0 volts. Well, the red isn't in 0 volts, and neither is the blue. So we always have two legs of the circuit. That's what these are called, legs. Leg 1, leg 2, leg 3. That is not in 0. So there's always a voltage differential between any two legs of the current. That becomes very important when we talk about motors. Because AC starts at 0, reaches a peak, and returns to 0, there's always a variation in voltage, and an effective value has to be determined. AC current reaches a peak at 90 electrical degrees. Okay, so again, we reach our peak at 90 degrees. We reach our negative peak at 270 degrees, again divisible by 90. This is known as peak voltage. The effective voltage of an AC current is 0.707 times its highest or peak voltage. Amperage is also 0.707 times the peak amperage. All electric meters are calibrated to reach effective voltage and amperage. They do not read peak. AC current is produced by an alternator. The alternator is made up of a winding and a set of windings called the stator, and a rotating magnet called a rotor. The number of windings used is dependent on the desired phase characteristics of the circuit. When the rotor is rotated through the field of the winding, an alternating electrical current is produced. So again, we have our winding and we have our magnet. Okay, so we rotate the magnet inside the winding, and that produces our positive and negative voltages, or our sine wave. The faster we rotate the magnets in the winding, the higher the frequency, or the hertz, of the current is. Three-phase current is produced by an alternator with 3 windings in the stator that are wound at 120 degrees apart. So each one of these is 120 degrees apart. We also have to worry about two terms called inductive and reactance. It's a common assumption that when voltage is at its strongest, amperage is at its strongest. This is not always the case. Amperage of a circuit determines the strength of the magnetic field of the circuit. If the current increases, the magnetism will increase. If a current decreases, the magnetism will also decrease. The fluctuation of the magnetic strength in an AC current and in conductors cutting through more than one magnetic field induces voltage that counteracts the original voltage. In other words, as we start a motor, or even sometimes a light bulb, this is why your calculated Ohm's law and measured Ohm's law measurements aren't exactly the same. Okay, but as we start increasing the magnetism that's part of AC current, it increases resistance, okay, which actually decreases current. This effect is called inductance. The inductance in an AC circuit is the effect of the magnetic fields which produces an out-of-phase condition between the voltage and the amperage. AC currents are affected by the resistance. They're also affected by reactance. Reactance is the resistance that AC encounters when it changes flow. There are two types of reactance in an AC current. In an AC circuit, you have inductive reactance and capacitive reactance. Inductive reactance is the opposition to the change in flow of alternating current, which produces an out-of-phase condition between voltage and amperage. Capacitive reactance is caused in AC circuits by using capacitors. When a capacitor is put in an AC circuit, it resists the changes in voltage, causing the amperage to lead the voltage. The sum of the resistance and the reactance in an AC circuit is called impedance. Power is part of AC current as well. When voltage and current are out of phase, they work with each other in an AC inductive circuit. They are not working together. Okay, thus the power of a circuit must be calculated by using a voltmeter and an ammeter. Power is calculated in watts. The ratio between true power and apparent power is called the power factor. The power factor is usually expressed in a percentage. This is the formula that can be used to calculate power factor of a circuit. True power, which is measured, divided by apparent power, which is calculated. So this is all the effects of AC current and how the sine wave works. Okay, again, the biggest thing to remember with AC current is 60 times a second, you are going to have a complete 360-degree cycle from 0 to 90 to 0 to 270 to 0 or to 360 or 0 degrees. In a 240-volt circuit, that's from 0 volts to 120 volts to 0 volts to negative 120 volts to back to 0 volts. That happens 60 times a second in the United States.